start out with a topic on building simulations of human behavior. So I'm going to spend about 20 minutes in order to build up to a sort of core idea that I want to convey today. These models of human behavior are being widely used, and I think it's an area of enormous opportunity for AI going forwards. They're being used in games. I mean, hitherto games have been largely formulaic in terms of, canned behaviors or very simple sorts of behaviors. But obviously, the idea of having richer behaviors informed by AI is a very exciting future for the whole games industry. And likewise, within TV, the future of television. Imagine you could actually immerse yourself in a Friends episode and actually participate in the episode, and it felt realistic, and you're actually interacting with the actors within the episode and becoming a part of it. And the story is evolving around you. So as you contribute, so the story evolves in order to respond to your contribution to the interaction. Now, this sort of stuff seemed like really fanciful 10 years ago, 5 years ago, but now, there's stuff happening which both in terms of the realism of computer graphics generation, but also in terms of the sophistication of the behavior models and the kinds of language models that are being developed, which starts to make this kind of thing seem like a much more realistic sort of possibility. Another kind of application for this technology is immortalization. There's a long history of immortalization, and by this I mean capturing the identity of a person, making them sort of virtually immortal in a picture, in a painting that goes way, way back, thousands of years, in a statue, also thousands of years, in a photograph, hundreds of years, just over 100 years, as a sound recording, again, back to the last century, and also video. This video here is actually taken in Roundhay, one of the first videos ever produced, Roundhay in North Leeds. And it captures something of the people that are depicted in these different things. Well, wouldn't it be great if you could capture the persona of a person? And this has been, it's been seen in things like, different science fiction movies recently and TV shows recently, capture the likeness of a person and the way in which they behave, the facial expressions they make, so that you can interact with them for all time. So you're capturing not just a video, a static thing of somebody that just is always the same, but something as you interact with it that actually varies. So this is, I think, a really important frontier for work in research and artificial intelligence, and a very exciting area of many, many different kinds of applications. But the problem is, how do you model the scale and complexity of these behaviors, both at the high level, the language structures, the way in which people behave, the facial expressions they make, down to the detail of the rendering, what somebody actually looks like and the way that the face changes as they make various utterances, or as they scowl or smile or whatever it is they might do. What about their hand gestures and the way in which their body moves as they're talking? How do you capture all of that richness? Well, surely one thing you can't do that by writing programs and rules, which is the way that people started out thinking about this. You do it by hand, essentially. You engineer it by hand. And of course, the way of doing it is to use machine learning. And that's been the story within this kind of area of the last 10, 20 years, is developing machine learning approaches to doing precisely this. So here's some work that we did over 20 years ago. I mean, we did this at Leeds. Neil Johnson and Aphrodite Galatu, who are both PhD students at Leeds, worked on a simple model that enabled you to shake hands with a virtual outline. And it was trained on real people shaking hands. And then you could come in, stand in front of the camera, shake your hands, and it would create this contour on the right that shook hands in response to you. It was interactive. It was incredibly simple. Basically, it was just based on the probabilistic model that drove this was something that was all the rage around 2000, which was deformable shape models, which was basically essentially based on principal components analysis of simple geometric shapes. and it became extremely widely used. And all we did was put a Gaussian probability distribution over this. I think it was a hidden Markov model, in fact, and we're able to create this kind of thing. And here's something that's just appeared 2 or 3 years later, where we trained up a model. Again, it was an HMM, hidden Markov model. So just very simple Gaussian mixture kind of representation, but with a temporal component. Looking at the facial expressions of two people interacting. It wasn't trying to model the sound or the speech or anything. It was just modeling the facial expressions. And so as this person speaks on the right, the computer can render on the left a face that's just responding to the facial expressions of the person on the right in a real interaction. So this was kind of, for me, was the point at which we started to think about using machine learning to capture behavior. And you could sort of see the power of this, even though these models were incredibly simple. So much more recently, James Charles at Leeds, working with Derek McGee, worked on Friends television shows and trying to capture what happens in Friends TV shows. And I've spoken about this before, so I'm not going to labor this today. But we took the whole box set of Friends and we tracked all the individuals, so we could actually track all the faces of the people in the show. We were able to find out their names because we had the scripts. So we had the facial expressions, we had what they'd said, the utterances. We used a very simple language model based on a recurrent neural network to model the language structures that the different actors were using. And we also pulled out computer graphic or just small videos of the mouth shape as somebody spoke. So in short, we could produce a model for any of the actors in the show. So we could capture Joey, that particular character in the show. We could capture Joey, the way he spoke, the way he appeared throughout the whole box set. And then you could actually generate totally original stuff that Joey has never actually said, but actually conforms with the language model that we produce, which is a recurrent neural network. And then render on top of a piece of video that mouth structure and with Joey actually speaking. And so we can do things like this. And I think I'm probably going to have to just do this up here. We could get Joey to speak like this.
Oh my God, I can't believe it.
So, you know, that was sort of generating proof of principle. You could take existing material, a box set, and generate, you know, not very realistic, but not particularly good graphical rendition. But it's Joey never actually said that in the show like that, and this was something that was generated by the language model, and then the graphics was generated on top of that. Well, since we did that in 2016, things have changed hugely. The whole field has gone through a bit of a revolution, and one of the first things that I became aware of, or we became aware of, was in the rendering area. There were loads of people around the world trying to produce high quality renderings of faces using 3D models in particular. So there were sort of synthetic computer graphics faces. And what was produced by NVIDIA was this extremely well-known now StyleGAN system, which generates very realistic faces, not by using a 3D rendering tool, but by using generative adversarial networks to actually generate the 2D picture directly by understanding the structure of the features that make up a face at all levels of very fine to very large features, and the way in which those things can be put together to produce a face image. So it's just a convolutional neural network of a particular kind, or it has convolutional elements in it. Of a particular kind, it's kind of layered, it's multi-resolution, you gradually increase the resolution, and you produce these unbelievable faces. So what can we do with this kind of model? This took 3 months on one GPU to train the original model, but the actual process of producing a system that works and going through all the meta parameters, you know, that's once you know what the parameters are, it takes 3 months to train. But when they started out on the project, they've actually burnt up 51 GPU years in order to produce this model. So it's unbelievably expensive to actually produce these kinds of quite AI systems which are based on very large data sets. well, this one's not so large. It's 70,000 images actually from a Flickr face data set of high resolution images. Given that, what could we do? Could we improve the graphics in our system? And so Mohammed, who's sitting here in the audience somewhere over here, and we'll be talking later on this, so I'm not going to say very much about it, has been working on a system that tries to improve the audio in the kind of Friends type application that we talked about. So you start out with an identity image, which is shown on the left, top left there. So it's just a picture of somebody, and you provide it with an audio clip. And what it does is it animates the video. So it sticks the identity image through an image encoder, and then it sticks the audio clip through an audio encoder, and then it combines the output from those two things. And crucially, what it then does is it puts the output into StyleGAN. So it maps it into the input. StyleGAN is driven by a random vector, which is 512 in size 512. And so what Mohammed does is he generates a 512 vector and stuffs it into StyleGAN. And so the result of that is you get this really high quality, potentially, image coming out. So here's the kinds of outputs that he's able to get. And he'll show other examples in his talk. So now one can produce much better rendered facial talking heads using the kind of technology that's coming. And of course, NVIDIA are obviously working on video generation as well. And there's just hundreds of people, if not thousands, working on this kind of topic worldwide. But Mohammed's work is going to be presented at the ACO Multimedia Conference later this year. This is a first in that kind of capability. So simultaneous with all this, the other huge thing that's been happening and that has been widely publicized is the production of real industry standard language models. And these language models essentially are just probability distributions over token sequences. If you have typically the token sequences can be 2048 or 8192 long, and you end up with what you get is you give me a token sequence and up to a certain point, and I'll tell you the probability for the next in the sequence. Or by multiplying all these things together, you can actually get a joint probability over any sequence for token sequences, where tokens are characters, words, or partial words. The most well-known is GPT-3, which appeared a couple of years ago, 3 years ago. This is actually trained on a large proportion of the text on the web. They eliminated stuff that was just gobbledygook, but they kept a lot of text from the web, and it's got 75 billion parameters. And the kind of thing it can do is this: you feed in top left there, you feed in the text that's in blue, title, stars, tux, promise, draws, etc., finishing with article, colon. You feed that in, and then you ask, what's the probability distribution over the next token? And it comes back and it says, well, A has a high probability. Or maybe they were all equal probabilities. It just chose something. It just chose A. So when you've done that, you then tack A onto the end of that sequence that's in blue, and then it will come back and it will say, well, year has quite a high probability out of all the things I could feed back. It has something like 32,000 different tokens, which are characters, words, and partial words. So year might be a token, for example. But when it comes to things like Phoenix, it might be Phoenix as two separate tokens. So it builds up the utterances like this. So it generates everything in red you see there was generated automatically by the GPT-3 system. Okay, so that's very exciting, and I'm sure we'll hear more about that during the conference. One of the remarkable things about GPT-3 is not only does it enable you to generate sequences like that, but you can also do stuff that I think must have been quite unexpected to the people that developed the system originally. So for example, you can do machine translation. Now, to do machine translation properly, you would actually use a pair of the so-called transformer architectures. And one which encodes the French utterance or the English utterance, and the other that decodes into the English utterance. But it turned out that with GPT-3, you could actually do translation directly using just this language model and not some fancier setup. So what you would do is you would put in the window for GPT-3 this sequence here. You convert it into tokens, translate English to French, comma. Not sure how important that little pre-utterance is, but anyway. And then you would say, given an English utterance. So this is giving an example. Would you like breakfast? And then some kind of symbol, which I've just put as an equal sign and a right arrow, voulez-vous un petit déjeuner? And then next line, it is raining. We probably want some sort of terminator after the déjeuner, actually. Maybe we've got a new line there, but you probably want something. And then it is raining goes to il pleut. The il pleut is generated by the language model. So that's just prediction. And so what's happening here? This must have been, when they discovered this, it must have been fairly amazing. What's happening is, I think, it's actually finding syntactic structure above the level of the sentence. It's finding syntactic structure in English prose generally that produces things like lists with separators between different parts of the list. And so the first bit here, is recognizing, I'm sorry, I'll go over to this screen here. It's recognizing that you've got this kind of sequence appearing. And at that high level, this is sort of training. It gives it sort of sets it up, and it sees that there's this thing here, and then it sees that this terminates with that symbol there, which is the same as the symbol there. That could have been any symbol probably. And the syntactic structure, the high level syntactic structure of the prose says, oh, English and that, and then it's French and then English. And just that syntactic structure enables it to actually produce a French utterance just where you'd want it. And so lots of interest at the moment in actually trying to make that, what else can you do with these language models? Once you've got a language model, you can do, it seems that you can do lots of stuff that perhaps was really unexpected. And so onto the scene, that was from One AI 2 years ago. And now this year, just in January, we hear about Lambda, which has been in development at Google for a while and has been in the press recently with one of the Google employees who claimed that this thing may be sentient, and for a whole, probably not directly connected with that for other reasons, has just lost their job. This Lambda system is actually the same thing. It's a language model, except it's about dialogue. And so that's really interesting for the friends kind of scenario where you're actually trying to enter into a conversation. It's a language model for dialogue. So it's just a probability distribution. It's exactly the same. It's the same model. It's a transformer model, which is this new style of neural network. It's got 173 billion parameters. It's trained on 1.5 trillion words or tokens of public dialogue and web text. Sorry, it's words. It is actually words, not tokens. It's split into tokens. And then, crucially, one of the problems is if you do that, you end up with fairly boring dialogue. If you just do what I've described there, the dialogue's not great. So what they do is the innovation in Lambda is they add another step, which is to present the general public through crowdsourcing online. They present the general public with utterances and get them to rate with dialogues and get them to rate the responses of the Lambda system. So is this any good? Has this sort of wandered off track? That additional thing, and by the way, what's really interesting about the way they do that is they use the same kind of in-window mechanism. It's not an additional kind of classifier or something that rates things. They actually train by doing it in the window of the language model. So it's just using the language model and tuning the language model to actually generate these dialogues. This is a transformer. If you're not familiar with transformers, a transformer is essentially, you have a lot of inputs, which is all this sequence of tokens, and you compare every single token with every other token, normally just going into the past, but just conceptually think of it as comparing with every other token. The strength of the match then determines how much of a weight associated with those other tokens gets added into something that replaces that first token you started with. You just do that through everything. So everything gets compared with everything. And so if you're trying to build up grammatical structures and learn about things like that, it's a very kind of intuitive that it works. It's actually able to generate these grammatical structures and these probability distributions. The transformer here has 64 layers, and it's actually 8192 wide, so it's quite a wide context window. It can deal with probability distributions that are as long as 8192 tokens. Now this was trained on 1024 TPU version 3s. Now the TPU is Google's tensor processing unit, to be aware. Version 3, this is what, 10 times faster. It's a lot faster than a GPU, as a conventional GPU. So they had 1024 of them crunching away for 57.7 days. That is an awful lot of compute power has gone into training this system. The power consumption was 451 megawatt hours, which sounds like a lot, but actually it's not. It's much less than you would think. If it was GPUs doing it, it would be a lot more than that. I think the TPU is much more power efficient, probably, at least for the same power. And what that equates to is 26 tons of CO2 equivalent emissions, which is the equivalent of 22 people flying return from San Francisco to New York. So these models consume a lot of power and generate a lot of CO2 emissions in order to produce them. But that kind of compute facility is more than you would get on, say, ARC4 or Jade or anything else. ARC4, ARC3, ARC4, yeah. So that's Lambda, and then of real interest to me was just in May, and the announcement by DeepMind, that was from Google Research, DeepMind, also part of the Alphabet family, of system Gato, which is the same thing, except that the tokens now are not language, not just words of a language, but it can be, the tokens can also range over images, chunks of images. So you split an image up into chunks and you produce tokens that represent the chunks of the image. It can actually be button pushes in a game. So, I have the left controller and I go press, press, press. That's a token. And whenever that appears, whenever I press, the token appears. So if I'm in a game and this is what's happening in the game is represented by a stream of tokens. And then I push a button and that token goes into the stream and then the game continues. And so Gato is actually modeling game sequences. And also a robot actually doing a stacking task. So a robot is moving, doing a stacking task. And this is one transformer. So they're training a single transformer to do this. So it's not trained with, it's not 4 separate transformers. It's actually one transformer with a set of tokens that range over all these different kinds of things. And this has got 1.2 billion parameters. It's not as big as the biggest in those terms, but it's really interesting because it's multimodal. It's actually ranging across different tasks. They're all interactive. These tasks are all about time and sequence and interaction between people in a conversation or whatever it is fits very nicely into that. So that's, I think, a very interesting development. And, it's obviously going to be, imagine what you could do with such a model, what kind of applications you could think about building if you had such a model. So, we're going to see undoubtedly over the next few years, lots and lots of work taking these models as pre-built things and showing what you can do with them. I think it's unrealistic to think that we can actually train those models ourselves. We might be able to adapt the models, but being able to train them ourselves from scratch just requires so much compute power that research methodology will be that we will use the models as they're given to us and see what interesting things we could do with them. And so just a little advertisement for a talk that's coming up from Fang Jun, who's sitting here, who's going to talk about one such application using a system called Glide, which is another of these kinds of transformer-based models in the imaging domain. And she'll in one of the parallel sessions later today, talk about the way in which you can use that to do something that people have been trying to do in other ways for some time. So now I'm going to just look at, that doesn't mean, of course, that, there is still huge amount of innovation in the machine learning area that we can, I think we can still participate, it still needs doing outside the appearance of these huge models that are, potentially very powerful. So I'm just going to talk about 3 or 4 things that are happening at Leeds for the next 10 minutes, just to set out the space of that. And first of all, it's Jose's work, who's sitting over here, and Jose's been looking at mouse tracking for biological research. And the aim is to actually produce a much richer description of the way in which the mouse pose is configured in each frame, because that, through having a much richer representation, you may be able to discover more about the particular behavioral, the phenotypic properties of a particular mouse. So this is all part of work on genetics and Parkinson's, Alzheimer's disease and the onset in humans, working with the University of Tasmania. And the innovation here is, in order to get this better pose model, is something that we're seeing cropping up in quite a few different places at the moment. And this is the idea of taking a neural network and implanting into the network a program which is not a neural network, but is a program that can be that's differentiable. So you can actually differentiate through the code, and therefore you can optimize the whole network with that code in place. And the way it works here is that you take, on the left-hand side there, a picture of a mouse, a single frame. The first thing you do is you have a neural network, a convolutional neural network that skeletonizes the mouse. It produces an image in the form of a skeleton. So this is a 2D image. And then you have another neural network that actually takes that skeleton and generates the positions, just a list of the positions of the joints within the skeleton. So that's an incredibly terse representation of the mouse. And then from that, you then use computer graphics to render the skeleton again. And having rendered the skeleton, you then finally use another CNN that takes an identity image in the top there. That's the thing at the top right, takes just a static picture, and it renders the mouse on the right. And hopefully the mouse that comes out on the right looks like the mouse that went in on the left. So the innovation here is to use a renderer in the pipeline, and then when you're optimizing the neural network, you're doing back propagation on the neural network. You actually back propagate through the renderer, and this idea is cropping up all over the place at the moment. The loss function to train this, the thing you optimize is the difference between the input and the output image. Did it get it right? So it's a bit like an autoencoder. Well, it is an autoencoder in that sense. And then also, top left there is an adversarial loss, which is looking to see whether the image that's been generated, the skeleton image that's been generated from the first CNN is actually a realistic looking skeleton. So there's a bit of sort of prior guidance in there. And this is the kind of thing you can get very high quality renderings of pose tracking of a mouse in motion. Some other work in biological sciences looking at the tiny worm, the C. elegans. This is in Netta Cohen's research group. And she has collected, over in the Bragg building, she's collected with her team this tiny worm crawling in an algae and or in a sort of gel. And she's recorded it with 3 high-resolution cameras over hours and hours and hours. And then using simple computer vision sorts of techniques, and they've got 2 or 3 different techniques that they've been exploring, able to generate a 3D reconstruction of this mouse. And then what you can do then is you can actually generate a 3D pathway trajectory of the mouse. And if you can see the mouse kind of moving through this structure over time, and through doing this kind of thing, now suddenly Netta, who is working in the sort of biological sphere, is able to think about the way in which C. elegans moves through these kinds of structures. It's got a very simple neural, something like 120 or 130 neurons make up the brain of this C. elegans. How are those neurons controlling the motion? What kind of motion do these things have? And there's a massive community worldwide of tens of thousands of people working on this tiny creature, the C. elegans. And they want to know, how does the C. elegans move in 3D? And this work is able to illuminate that for the first time. There's been lots and lots of work in 2D. Doing it in 3D is a whole different kettle of fish, and doing it at scale in 2D. Here's work from Claire Bartholomew, who's a part-time PhD student with the Met Office. And she's been working particularly around London, looking at airflow around London, aircraft coming in, and trying to predict when there's going to be a downfall of rain, which is sufficiently severe that you need to divert aircraft from Heathrow to Stansted or whatever. So it's trying to do nowcasting down at the 10-minute level, predicting when rainfalls are going to occur. And in order to do that, using the weather radar system, which is a set of radars around the country, which look at precipitation, or are able to measure precipitation in the air across the whole of the United Kingdom. And there's similar networks across Europe and the other parts of the world. And it produces these kind of rainfall pictures on the right. And so the challenge is, can we predict forwards for a few minutes, in this case, just 10 minutes, what's going to happen in the future? What's the precipitation going to look like? So the idea is you take K previous radar frames and you feed it into the first obvious thing to do is to feed it into a UNet architecture, which is an encoder-decoder CNN. So it's just a convolutional neural network that squeezes it down and then expands it again. It encodes it and it decodes it, and it's got some crosslinks. And that's the UNet. So it's the encoder, decoder with crosslinks between the two, which hence the UNet. That's the sort of obvious starting point, and that's where Claire started. And she's able to predict the radar frame. And you can see on the right there, it's a reasonable prediction. The trouble is when you go to 20 minutes ahead, prediction gets much fuzzier. And this is one of the problems with this technique. Because the underlying process is stochastic, there are many possible futures. Just because you know K frames up to the current time, what can happen next could go in many different ways. And unfortunately, when you train up a UNet to do a prediction, you try and predict the future, it just tries to splay over all those different ways. And so you end up with a fuzzy future, a blurred future. So a better way of doing it is to use a technique that appeared in 2019, which is to do something very similar, except that you feed in a random variable. And so down the bottom there, you have the previous frames on the left, and down the bottom you have the prediction model. And then from the prediction model, you generate the frame in 10 minutes time. But you also have this thing in the middle, which is generating a random vector. And you stuff that random vector is actually dependent on the prior frames. But the key thing is it's a random vector. You stuff that in as well to the prediction. And what that does is it selects out just one of the possible futures. So you only select one of the futures using this latent vector. And the result is that using this technique, you can select a possible future. On the left there, we've got the radar, the actual radar. On the right, we've got the neural network predicting 30 minutes, 35 minutes ahead. And on the right, we've got the operational nowcast, which is the current prediction facility that the Met Office uses, which is based on traditional optical flow-based techniques from the computer vision image analysis community. But the nice thing about it is you can actually look at a range of possible futures. So you don't have to look at just one possible future. You can actually look at multiple possible futures. So this so-called ensemble approach. So each one of these, except for the bottom one, which is the actual radar, is a different possible future. And so you can look at all these different possible futures just by feeding in different random vectors. And you can ask, are any of them bad news for Heathrow Airport? Because if any of them are bad news for Heathrow Airport, then maybe you should transfer the planes to Stansted. So that's the benefit of this kind of technique. So again, an innovative technique, something a bit different from the usual neural network sort of approach being applied to nowcasting. And now some work that is being done by Tom Hazelhurst, who's sitting here, on engineering design and trying to find similar parts. So you have these engineering design parts on the top there, and we can represent, though, what we want to try and do is pull out of a very large database of maybe hundreds of thousands of parts, something that's similar to a particular part that we start with, to try and find out whether or not we've actually got something already in our database which is similar to something that we have. And so this could be really important for engineering designers. So how to do that? Well, you can very naturally take these CAD, computer-aided design models, and you can represent them as graph structures, where the nodes are the types of the faces, and the edges of the graph are the connections between the faces. What's the angle between the two faces, for example? What's the relative size between the two faces? So the first step then is to translate the hundreds of thousands of models in your database into graph structures, and then to use so-called graph neural networks, which are a type of neural network that's a generalization of a convolutional neural network developed for images and 1D speech waveforms or image-based data, a generalization to graph structures. The idea being that you update what happens at a node by looking at neighboring nodes, and you just do that repeatedly. So here's the structure of the network that Tom has built. You start out with a CAD model on the left, you map it into a graph structure. In this case, the graph structure has n nodes, each is of size 10. So it's a vector of size 10. And that's just an encoding actually of the type of the face. And there are m edges, whatever m is, and each edge is a vector of size 11, which encodes all the different relationships on the edge. And then you map that through a single iteration of this graph neural network. And the edge attributes, the 11 numbers you put in at the beginning, don't change. All that changes is the node attributes. And it goes from being a vector of size 10 to a vector of size 32. So this is now in a completely different space. And you just do that 3 times. Finally, you stick it through a linear network at the, at the end, you also take an average or an average of all of the nodes, the values of all of the nodes, put it through a linear network, and then finally map it to a 16-dimensional latent space. So there you have now, you've translated your hundreds of thousands of models into a 16-dimensional space using this graph neural network. And we can visualize what it looks like in 16 dimensions. And so here's a visualization. And you can see that in this example, which is just 70 or 80 parts, similar parts are indeed close together. And that means that we can very rapidly do a search in this hundreds of thousands of models. You take you take all your models, you take the one that you take a model that you've just discovered or you just built, you encode it in the 16-dimensional space, and you look to find all those models that are similar to it. And this is just illustrating that similar things are indeed close together in the space. And then finally, some work with Earth and Environment, just to show that you know, a workhorse for machine learning at the moment, and a lot of people, I think, probably across the university are using, is this UNet for image segmentation. It's been used in medical applications. It's been used in the environmental sciences. So here's some work from Benjamin Wallace in the environmental sciences, and what he's trying to do is to discover in Antarctica sedimentary flows from the base of a glacier. So if you look at a glacier, the white on the left-hand side there, that's a satellite image from Sentinel-2, and the bit of the coastline of Antarctica, which is this top left bit, the Antarctic Peninsula there. The white is the glacier, and the sea is on the left, the darker bit, and then on the right we've got a ground truth. So this is actually, that green area is actually a sedimentary plume. It's material from underneath the glacier that's been swept out into sea, and glaciologists are very interested in the extent of these plumes. So wouldn't it be great if you could take the whole of Antarctica and map the plumes on an hourly basis or on a regular basis every time the satellite goes over? And so that's what he's doing using a UNet that he's trained in order to predict where these sedimentary plumes are. And you can see in this case here, you probably can't see it very clearly, actually. It's not very clear on the monitor. The red, there are little red outlines, which are the predictions from the UNet. And the green is the ground truth that has been produced by hand. And actually, there are places where you can see that it looks like the UNet segmenter has actually found more of the plume because it sort of goes out into the ocean and finds new bits of the plume going further. So this is work in progress. But suddenly you can take the whole of Antarctica, Sentinel-2 satellite, and you can do this for the whole thing at scale using, he's actually using ARC4 to do it at the university campus. And that's really interesting to glaciologists, and there's just lots of that kind of work that I'm aware of going on across the university, both in environmental sciences, in medicine, and other areas. So I hope that's been coherent. I tried to give a big message, which is that these big systems like GPT-3 are necessarily going to have a transformational effect on the way in which we do machine learning, the way in which it happens globally in the research community. But there's tons of stuff still going on, obviously, in machine learning that's hugely interesting. And a large part of it is about representation. It's about the way that you actually represent things. And that's where the innovation is. It's not so much in a new kind of convolutional neural network or a new kind of transformer or a new kind of fully connected network. It's in new ways of using these things by representing information in different ways. And there's still lots and lots of really interesting and exciting stuff going on in those domains, including, I have to say, in the Doctoral Training Center for AI in Medical Diagnosis and Care, where a range of these models are being used for medical imaging. So thank you very much.
Thanks so much, David. That was an excellent keynote and really gets us off to a great start. We've got some time to take some questions. Do we have any questions at all? Sure.
Hi. Yeah, so this is being done with biologists at the University of Tasmania, and it's a standard sort of mouse facility that they have there, and obviously that's all been through ethics at the University of Tasmania. So I mean, yeah, I agree. Absolutely, yes. I think this will get much better value out of much more information from the information we have, and will hopefully result in therefore fewer mice being needed. Yes, yes. Hi.
So my question is about your first part. You talked about visual expression versus specific. Where do you see the industrial application of natural coding? Is required already in some way in the industry, or is it your teaching class?
Yeah, yeah. So I think it's a good question. I think it's twofold, really. One is there's just bound to be lots and lots of. It seems to me there's huge potential for things like that, Friends, taking part in the TV show, more interesting games, that whole sort of thing, and realistic faces. I mean, they do it now. They actually use older technology. The technology I used for that facial reconstruction with the two people talking to each other, that technology is, you can buy it in games and you can superimpose your face on an agent in a game, and that's well, and it's animated, that's well developed technology. But the other area must surely be chatbots and talking heads for a particular individual. Animating a talking head and making it look realistic, I think is must be an area of application. Of course, there are real downsides to this too, because the whole fake thing, making, if you put in somebody well known and feed them with an audio channel, you can make them speak in a way that's unnatural. Actually, the work that Mohammed's doing doesn't quite suffer from that because the audio is somebody else's audio. And so you can immediately see that's not Obama speaking, it doesn't sound like Obama. But, you know, a different way of doing this would be to actually translate the audio as well to make it sound like Obama as well as be Obama. So I think this is less problematic actually, but this is obviously a concern that it has to be used. It has to be used responsibly. But I think there's a wide spectrum of possible applications. But in industry today now, chatbots, I would say, is a lot of chatbots are just online. You know, they don't have a face or they have a cartoon face. But, you know, the idea of a visual chatbot, I think, is powerful.
What do you think about medical application for interpretation, how to interpret people affected by autism, for example?
Yeah.
What do you think it could be used there?
Yeah. Yes, I mean, I'll give you one medical application. I haven't. I'm sure that there would be interesting things that one could think of. I'm not aware straight off of something where that might. I mean, you can certainly detect. You might be able to detect problems by watching somebody's facial expressions, and that may give you some indication that maybe they're developing. So it's more likely with gait actually, human gait rather than the facial expression, but facial expression may give away an underlying problem. So that's certainly possible. But an area, a problem we've been presented with now from two different sources actually, is the idea of training doctors simulating the patient. There is a huge shortage of, huge demand for training, new ways of training a doctor. So the idea is the doctor would be able to have a conversation with the patient, but the patient's simulated, but realistic. And that's the challenge. You know, it's not, at the moment, Maudsley Scientific, who train doctors in mental health, they have actors playing the patients, hugely expensive. And it's a real bottleneck, because you have to, there's only a limited number of actors that they can use. So the doctors go to their facility, they meet with an actor for 20 minutes, everything's recorded, and then they have a conversation afterwards, and a group of people sit around and discuss how they behaved with the actor. Imagine you could actually simulate the actor, and that I think is a challenge. And we've been talking to them about the possibility of doing that.
I'm going to take one more, which is from Sue.
Thank you very much. I wonder what you think about the future of the industrial research. I think a lot of foundational models which require 1,000 hours of 1,000 IT degree, which is much more.
Yeah.
For example.
Yeah.
System.
Yeah.
So,
yeah.
So this is possible with industrial research at the same time.
Yeah.
The
Yeah. Well, I mean, it's going in the direction of big science. You can't build a particle accelerator yourself. You have to share and share it, and maybe that's the direction, more of the direction things are going. But it does feel a little bit them and us, but there is an awful lot that you can do, that one can do with the models that exist, and they are putting them in the open, in the public domain, so you can actually use them. Like, whether they're really public domain enough, we've been using GPT-3 in the public domain. To run it, you can download these systems and run it yourself, and I think that's certainly something that would be good. You can adapt the systems. Training StyleGAN only takes 3 months on a GPU. We could envisage doing that, but you've got to know you've got to know all the meta parameters. That's just one run to do one train. If you actually want to do a grid search on all the different possible meta parameters, then it's much more expensive than that. So that's still in the realms of possibility for us. But I think it's very interesting. Yeah, and this has only happened in the last 4 years. Suddenly there are models that we couldn't train ourselves, which are hugely interesting. We can play with them. We can think about using them in innovative ways, which is what we are doing. And they become maybe one way you can use them is treat it as a black box. And you know, if you want to build a system that has, I'm looking at something yesterday where somebody was doing something and they just wanted it to be multi-language. And so they were just going to use a multilingual front end and, you know, trivial, you know, just do that. Well, obviously, that would be unheard of a few years back. You wouldn't even dream of doing that, but now you could just pull it off the shelf, multilingual front end. Why not? You know, and this was actually in the context of robotics, you know, and I mean, that's interesting future. And I think we're still working it out.
Absolutely. Well, if everyone could put a hand again to David Holmes.
Thanks, Alex. Thank you. Oh, thank you. Cheers.
Okay, so the next session starts at around 11. So you've got 5 minutes or so to quickly nip up